Assalamualaikum. Welcome back to Sir K Labs Physics and Chemistry tutorial for high school students. In this episode, we revisit relativistic kinetic energy and use it to compute the relativistic speed of a particle traveling with a substantial speed comparable to the speed of light. So join me till the end of this video. Watch and learn. The question is, at what speed is a particle traveling if its kinetic energy is 3 times its rest energy? Let the speed of light, c, be equal to 3.00 times 10 to the 8 meters per second. Right? So, for our solution, we first define or express the total relativistic energy of the particle, denoted here by capital E. So this total relativistic energy, capital E, is just equal to the product of the rest mass of the particle times the speed of light, divided by the square root of 1 minus b squared over c squared, which is also known as the reciprocal of the Lorentz factor. All right, so the particle also has what we call rest energy. And this rest energy, denoted here by capital E naught, is just equal to the mass m naught times the square of the speed of light. So this equation for rest energy is exactly the same as Einstein's formula, E equals mc squared. And since the particle is assumed to be traveling with a substantial speed comparable to the speed of light, therefore we say that it has a relativistic kinetic energy, right? And Ka prime represents this relativistic kinetic energy of the particle. And it's just the difference, or the amount of the total relativistic energy, capital E, minus the rest energy of the particle, E naught. Or the relativistic kinetic energy of the particle, Ka prime, is just equal to the product of m naught, or the rest mass of the particle, times the square of its, or the speed of light, all over the square root of quantity 1 minus b squared over c squared minus m naught c squared, right? So the first term in the equation represents the total relativistic energy, capital E. And m naught c squared, of course, is the amount of the rest energy, E naught. And in this problem, all right, we are asked to determine the relativistic speed of the particle if its relativistic kinetic energy is said to be 3 times the amount of its rest energy. So moving on to our computation, all right, uh, we now express the relativistic kinetic energy Ke prime being equal to 3 times the rest energy E naught, or that is m naught c squared over the square root of 1 minus b squared over c squared minus m naught c squared, all right? That is the equivalent of the relativistic kinetic energy, or Ke prime. Then equate that to 3 times the rest energy, or 3 times m naught c squared. So when we start simplifying this equation, all right, we first move or transfer m naught c squared to the right side of the equation, all right, and get m naught c squared over square root of 1 minus b squared over c squared equals the sum of m naught c squared and 3m naught c squared, which is 4m naught c squared, all right? And then, uh, if you're going to cross multiply, notice that on the left side of the equation, we have this quantity, square root of 1 minus b squared over c squared, all right, in the denominator. So when this is transferred to the right side of the equation, and 4m naught c squared is transferred to the left side of the equation, this is what we get, right? M naught c squared over 4m naught c squared equals square root of 1 minus b squared over c squared. So obviously, we can cancel m naught c squared, all right? And get 0.250. That is the equivalent in decimal of, all right, the number 1 over 4. Then we square it. On the right side of the equation, we were able to get rid of the radical sign. So you're only left with 1 minus b squared over c squared, right? And then, if you're going to isolate uh, negative b squared over c squared to the left side of the equation, this is what we get. B squared over c squared equals 1 minus the square value of 0.250, which is 0.0625. Okay? So simplifying by transposing c squared to the right side of the equation and then getting the square root once again, this is what we get. V equals c multiplied by the square root of 1 minus 0.0625. That is, V equals c multiplied by the square root of 0.969. This is the difference, all right, of 1 minus 0.0625. And finally, when we get the square root of 0.969 and then multiply to the speed of light, we finally get the value of our target variable, the speed of the particle v, all right, equal to 2.91 raised to the 8th power meters per second in 3 significant figures. So this is the speed of the particle, so that its relativistic kinetic energy, Ke prime, will just be 3 times its rest energy. Let us try using another method in determining the speed of the particle using what we call the Lorentz factor. So gamma, which is the symbol for the Lorentz factor, is just equal to the reciprocal of the square root of 1 minus v squared over c squared. That means our formula for the relativistic kinetic energy, or Ke prime, all right, may be expressed in terms of the Lorentz factor. That is, quantity gamma minus 1 multiplied by the rest energy of the particle m naught c squared. And based on the problem, okay, this relativistic kinetic energy Ke prime, already expressed in terms of the Lorentz factor, that is, quantity gamma minus 1 multiplied by m naught c squared, is equated to 3 times the rest energy, or 3 times m naught c squared. And then we're going to solve for the value of the Lorentz factor gamma. All right. We can in fact cancel m naught c squared on both sides of the equation. So we're able to simplify and have gamma minus 1 equals 3. That is, the value of the Lorentz factor gamma is equal to 4. So, using the definition of the Lorentz factor, that is, gamma equals the reciprocal of the square root of 1 minus v squared over c squared, we can proceed and determine, all right, the value of the speed of the particle v. So, um, the equation, okay, will become 4 multiplied by the square root of 1 minus v squared over c squared equals 1. All right? So, in other words, what we did is just to cross multiply the square root of 1 minus b squared over c squared, being in the denominator, is transferred to the left side of the equation. Hence, what we got is 4 square root of 1 minus b squared over c squared, and leaving on the right side of the equation the value 1. And simplifying further, right? Squaring both sides of the equation. So we get the square of 4, which is 16, and the square of the quantity inside the radical sign will just be equal to 1 minus b squared over c squared, right? So we just got rid of the radical sign. But 1 minus b squared over c squared will be multiplied by 16 and then equated to 1. So further simplification by isolating v, or the speed of the particle, our equation now is reduced to v being equal to the speed of light c times the square root of 1 minus 0.0625, right? That is, after getting the square root of 1 minus 0.0625 and then multiplying it by the speed of light c, we finally get the value of the speed of the particle v equal to 2.91 raised to the 8th power meter per second, exactly the same as the answer that we got earlier in our first method. So that concludes my lesson for this topic. Till the next episode, mabuhay. Masya Allah. Thank you very much for your indulgence. Please don't forget to subscribe to my YouTube channel. Alhamdulillah.